Here we go. All right, so welcome to our first play posit of several for magnetism. We're going to be leaning heavily on play posits for the next couple weeks because we have a lot of material to get through. So please, please, please make sure you watch these. You may have to watch them multiple times. You can always refer back to them. So today we're going to be learning something called Ampere's law, as well as using the right-hand rule to determine the direction and magnitude of magnetic fields. And if you're looking at Ampere's law and thinking, that sounds an awful lot to me like Gauss's law, you're not too far off. They are similar in some respects and relate to each other in a very nice way. We are going to be using Ampere's law in a similar way. So we're going to talk about where does magnetism come from? What is a B field? B field being B for magnetic, because of course there is no B in magnetism. How to use your right-hand rule. We're going to use it many times over the course of this unit, but we're going to get a feel for how to start. And then we're going to deal with Ampere's law and apply it in a couple different cases. All right, and the big thing here that we want to, we're going to get a couple other understandings, but one of the big things we want to talk about with magnetism is that where does magnetism comes from? It comes from current. It comes from moving charges. All right, so here we go. Well, here's a little animated GIF. It is a little slow. If you just have a little spool of wire connected to a battery, and you've probably done this at some point, if you hook it up to some current, it will pull up paper clips. It will attract things. There's nothing special about this wire. It's just a loop of wire. It's got a little chunk of metal in the middle, but the chunk of metal actually is not necessary. If you run current through a wire, what you will find is that metal will start to move. And this is a little mysterious because we are putting electricity in and we are getting magnetism out. And this is our first biggest piece of evidence, and was a piece of evidence in history for the idea that moving charges give rise to magnetic fields. So anytime we have a current, we are also going to have some amount of magnetism, some amount of magnetic field. All right. But you're used to a lot of things that don't require current. So here's a permanent magnet, and it's festooned with paper clips. What the heck is going on here? Are there moving charges? There's a B field. Does that mean there's moving charges? And the answer is, yeah, there's moving charges. And those charges are moving in a couple ways. One way that we find moving charges is we have electrons orbiting around our nucleus. Now, remember, electrons are negative, and so if the electron is orbiting this way, the direction of current is actually the other way. And what we're going to find is that that rotating electron gives rise to a magnetic field that points kind of in the upward direction, as you see. We'll talk a little bit more about why north is at this end and why south is at that end, but suffice it to say, just like electric fields went from plus to minus, B fields go from north to south. So the electron creates a current kind of as it moves around the nucleus, and that generates a magnetic moment that generates a small amount of magnetic field. This actually turns out to be a rather small contribution to the overall magnitude of magnetism in a material, but it's still there. You get some current, that turns into a magnetic field. What we find is actually stronger is the inherent spin of the electron. Electrons, if you observe them closely, they appear as though they are constantly spinning. They appear as though they are like rotating around some axis. And this is something you might remember from chemistry called the spin. They can be spin up or spin down. They are not literally spinning. This is not exactly what's going on, although it's a good way of thinking about it. And one of the reasons they're not actually doing that is, as far as we know in physics, electrons have no size. So how can something that has no size be spinning? I don't know, but it is. It has some intrinsic angular momentum that we call spin. And this spin, similarly to moving charge, generates a magnetic field. And so what we find in most materials, though, is that if you look at all the electrons, their spins are all in different directions. The little atomic magnetic moments that you get point in all different directions. In many materials, and again, you might remember this from chemistry, you actually find that all of your electrons are paired up in their shells, and so their spins cancel each other out. And these materials have few magnetic properties. However, in some materials, such as what are called ferromagnetic materials. All of those little domains, all those little sections of all those little moments from electrons line up. You got all your moments. They're all lined up. They're all working together in the same direction, and you get this bulk magnetic field. Whereas, you kind of imagine this as like a crowd of people milling around. They don't really get anywhere. This is a crowd of people all walking in lockstep. They get to move together and do something great. So in magnetic materials, all of those little spins are lined up, and so our material develops some bulk magnetism. It's a little bit more complicated than that. Usually what you actually find is you get these little domains, these little kingdoms, and within a little domain, you'll find that all the spins are lined up. But that domain to domain, they don't all line up. But again, if you magnetize it properly, what happens is that all of those fractured domains, all of their spins line up also. If you can get them to line up, they can work together for the good of the common magnetic field. So you need that state of order in order to get good magnetism, strong magnetic field. As you might be aware, similar to electricity, like poles repel, so two north poles will repel each other, two south poles will repel each other, but a north and a south, it's love at first sight. They will attract each other. All right. You will notice, by the way, that our electric field lines, our magnetic field lines, and we'll see this a little bit more, are always going to kind of make a little loop. They're going to come out the north end of the magnet, in through the south end of the magnet, and then internal to the magnet, they will kind of proceed the other way. They always make a nice loop. One of the consequences, though, of all these things being lined up is that you can never isolate just a north pole of a magnet. If I take a north and a south and I cut it in half, I don't get one north pole and one south pole. I actually get two magnets that each now have a new north and a new south. There's actually some evidence to suggest that we can talk more deeply about this if you're interested, that nowhere in the universe does there exist a magnetic monopole. That's the classical theory, is that you never will find just a magnetic north sitting around, that every north comes with a south. Every north comes with a south. You always get a north pole and a south pole together. So that comes up sometimes. They'll ask you on the AP test, what happens if you cut a magnet in half? In 1819, Hans Christian Ørsted, not Hans Christian Andersen, different guy, discovered that a current carrying wire will deflect compasses, will deflect them and kind of in a little circle around the wire. And this was our first inkling about the connection between electricity and magnetism. Specifically, it also told us something about the shape of a magnetic field. And what was developed was this idea that the magnetic field circulates around a wire like this. And you can use the right-hand rule to figure it out. If you point your thumb in the direction of the current, take your right hand, the way your fingers curl tells you the direction of the field. So again, thumb goes with the current in a straight line, and the curl of your fingers tells you the magnetic field. And again, I'm using the letter B for magnetic field because that's what we use. So again, you can get this shape, but we're going to find that these fields are generally in 3D, and it's very hard to draw 3D things on a 2D sheet of paper. So as we're discussing these magnetic fields, we're actually going to develop a slightly new notation, which we're going to see all the time. We know how to draw vectors left, right, up, and down, but it will be important sometimes to get vectors that go into the page. So if you're looking at your computer screen, imagine an arrow coming out of your face and going right into the screen. And just like an arrow, if an arrow is going away from your face, you would see the tail feathers of the arrow. So for vectors into the page, we like to draw X's. And for vectors out of the page, well, if that arrow is coming right at your face, all you're going to see is the point of that arrow. So those are vectors out of the page. So if you need to go draw into the page, you use X's. Out of the page, you use dots. And so we can kind of sketch out our fields a little bit differently like this. So here you can see we've got a current carrying wire. That current is going, let's see, it's an X that's going into the page. So if you take your thumb and you jab your right thumb at your computer screen, point it directly into your computer screen, you should find that the fingers of your right hand want to curl in the direction of the magnetic field that's shown. So this is one of our second important rules, that if we put our thumb in the direction of current, our fingers will curl and show us the direction of the magnetic field. In fact, right, so this is one of our big important things. We're going to see lots of right-hand rule. So make sure you know this for magnetism. In fact, what we're going to find is that we can figure out the direction of our magnetic field with the right-hand rule. But the strength of that magnetic field, as it says down there, the strength of that magnetic field for a lone wire is going to be some constant number, mu zero, kind of like epsilon zero, but it's a mu, over 2 pi times the current divided by how far away from the wire you are. And so what we find is that if we look at the strength of our magnetic field versus our wire, here's the radius of our wire, because our wire has some real thickness. Outside of that wire, the magnetic field drops off with distance as like 1 over r. As that d gets bigger, as we get further and further away, the magnetic field drops off as 1 over r, which again, if you were remembering from Gauss's law, you might be like, oh, well, of course it's 1 over r. It has cylindrical symmetry, which we often found with Gauss's law. We got 1 over r. Yeah, but in any case, we can't use Gauss's law here. This isn't an electric field. So where did this come from? How did I get this equation randomly? I will say this equation, they expect you to know on the AP exam. So they do expect you to know this equation on the AP exam. That said, we're going to find out in a moment how to derive it for ourselves. So for the moment, let's just try to use it. What is the strength of the magnetic field if we are 0.2 meters away from a wire carrying 2.5 amps of current? Notice here that mu zero, I'm giving you the value of mu zero, which is 4 pi times 10 to the negative 7th for this. So go ahead and try to calculate B using that equation. All right, well, let's try this out. So we're going to get B equals, well, mu zero, I just told you is 4 pi times 10 to the negative 7th over 2 pi. I is 2.5 amps divided by 0.2 meters. So let's see, I can do a little bit of division here. 4 pi divided by 2 pi is just 2. So let's see, that's going to give me 5 times 10 to the negative 7th divided by 0.2, which is, I know, 1/5. So I should get like 2.5 times 10 to the negative 6th for this. So let me just check that with a calculator, and I should have had a calculator at the ready, but I didn't. So we're just going to do 2 times 10 to the, 2 times 10 to the negative 7th times 2.5 divided by 0.2, and we do in fact get 2.5 times 10 to the negative 6th. 1, 2, yes, excellent. And what is our unit here? Our unit actually happens to be this little capital letter T, which means Tesla. So 2.5 times 10 to the negative 6th is the correct answer. What is a magnetic field measured in? It is measured in Tesla, which is also a Newton per amp meter for reasons that we'll discuss later, per amp times meter. It is in Tesla, named after this Hungarian gentleman over here. And of course, we also need this constant mu zero, which is similar in role to epsilon zero. Epsilon zero was that interesting constant for electric fields. Mu zero, 4 pi times 10 to the negative 7th, is the interesting constant for magnetic fields, and is called the permeability constant, or the permeability of free space. So just to take a look at this, some of our typical field strengths here. The surface of the Earth, rather weak, 5 times 10 to the negative 5th, so not a whole lot stronger than the wire that we just found. Refrigerator magnets, about 100 times stronger than the Earth, which makes sense because I can stick something to my refrigerator and the Earth can't pull it off. Laboratory magnets can get quite strong. We've got some quite strong ones that I'll show off to you in class. If you get to an MRI or a superconducting magnet, you can easily get like 7 to 10 Tesla. And I just want to point out, 7 to 10 Tesla is ridiculously strong. It doesn't take a whole lot more than that to begin like ripping apart matter. You can use these superconducting magnets to literally levitate a live frog. So we might take a look at that. But a Tesla is a really, really big unit. All right. What if I have a more complicated wire? What if I bend my wire around in a little loop like this, which often happens? You know, you think about that electromagnet we saw before, and it was like a little coil of wire. Well, what we find is that the right-hand rule still makes sense in a lot of places. Down here, I have my current going, if I take a cross-section of my wire, my current's going into the page. And so I'll get loops that go in the clockwise direction. On top, my current is coming out of the page, and I still get loops that kind of move in a counterclockwise direction there. And what I think is kind of neat is there's actually a different version of the right-hand rule we can apply for loops. So here, if you imagine taking the fingers of your right hand, and if you curl your fingers with I, so if you curl the fingers of your right hand in that counterclockwise direction, then your thumb points it with the magnetic field, at least in the middle. So here, if our right hand goes counterclockwise, our right thumb is pointing out of the page at us. So there's kind of these two versions of the right hand rule. And again, here's that picture of our field for it. You still might ask though, how can we calculate B? How can we actually calculate our magnetic field? Well, it's going to depend first on understanding something called a line integral. So a line integral is like an integral for a vector field. You're going to walk through a vector field, and what you're doing is you're adding up everywhere along that vector field how much of your vector field actually points in that direction. So you're going to kind of walk along your curve here, and at each point in your curve, you're going to ask, well, how much is my magnetic field pointing in the direction I'm moving? So here, it's pointing fairly well in my direction of motion. Over here, my direction of motion is here, and my magnetic field is not pointing so well. So we kind of add up the contributions of our magnetic field along this line. The details of line integrals are quite interesting. We're actually not going to delve deeply into line integrals, though, in this particular unit. Instead, kind of like we did with surface integrals in Gauss's law, we're going to cheat a little bit. What we're going to find is that either our magnetic field doesn't go along our curve at all. Our magnetic field is always perpendicular to our curve. In which case, well, how much of our magnetic field points in the direction of the curve? 0. So either we're going to get everywhere perpendicular, and it's going to be equal to 0, or it's going to be everywhere parallel, in which case it's just B times the length of our curve, B times L. So kind of like with Gauss's law, we get to elide some of the mathematics, at least for now until you get to college, and say that our line integrals are always either going to be 0 or just B times L, in the same way as we had for flux, where it was usually either 0 or E times A. All right, so Ampere's law is this really excellent rule that says if I have some wire, if I have some current carrying wire, and I want to know what my magnetic field is, what I can do is I can sketch an Amperian loop, which just like a Gauss's law is a closed loop, although in this case it's not a surface, it's just a loop. It's a 2D figure, it's just a loop, usually a circle. So we're going to sketch an Amperian loop, and we're going to take the line integral of our magnetic field along that loop. So we're going to declare an imaginary loop and take our line integral of B around it. So in this case, we can find out that, okay, well, it's everywhere tangent. So it's just going to be b times the length of my loop. I happen to know that the length of my loop is just the circumference of that circle, which is 2 pi d. That's good to know. But you remember for Gauss's law, there was a second side. Our flux was equal to something. Here, what's this line integral equal to? Well, Ampere's law tells us that that line integral is equal to mu0 times the current enclosed. It's equal to mu0 times the current enclosed. Did I have a separate slide for this? I did have a separate slide for this. Mu0 times the current enclosed. So this is Ampere's law. The line integral, and again, they remind us that it has to be a closed loop of b over our curve equals mu0 times the enclosed current. So again, Ampere's law tells us about the relationship between that line integral and the current inside, and if you can exploit symmetry, it'll tell you something about our magnetic field. And again, here in this case, our wires 2, 3, and 4 all go through the loop. Wire 1 does not go through the loop. So let's try this for our single wire. Well, okay, remember we said that the line integral here, it's always going to be tangent. So this would be b times L, or we decided b times 2 pi d for an Amperian loop of radius d, equals mu0 times, well, how much current is enclosed? Well, in this case, our whole wire goes through our Amperian loop. You can kind of imagine that we've drawn our Amperian loop around the wire like that. All of it goes through, so we just get I. And now if I do a little bit of dividing, my 2 pi comes over here, and I get, oh look, that's the equation that we got from before. So that's where it came from, is using Ampere's law. So again, you don't necessarily have to memorize this equation, but you will need it for the AP exam. So you either better memorize it, or you better be able to use Ampere's law to go get it when you need it. All right. One last thing I want to talk about on this play posit is solenoids. A solenoid is basically a coil of wire. It's an electromagnet. It's usually a helix. It's usually made of circular coils. And because it's all in series with itself, the current is constant. Very big solenoids can have hundreds or thousands of coils and can make a very, very strong field. And we're gonna say the magnetic field right on the inside is very strong, and you can kind of see from the diagram is very uniform, is a very straight line. We're actually going to pretend often something kind of important. Sort of like we did with Gauss's law, where we sometimes pretended things were infinitely large so we could, our parallel plates, we assumed the electric field in the middle was constant, which it mostly is. We're going to pretend for solenoids that on the inside, the magnetic field is totally constant, never changes, has the same value. And on the outside, we're actually going to pretend that there's no magnetic field. So we'll get to that. Okay. Why are solenoids so strong? Well, if you start adding up multiple loops, your magnetic field kind of builds on itself and builds on itself and builds on itself and builds on itself. So you can see it kind of amplifies its own behavior. The field in the center is strong and parallel to the axis, whereas the field outside the loops is pretty much zero. So we're usually going to pretend for a solenoid that the magnetic field outside really just is equal to zero. So this is our ideal solenoid. And again, nothing in real life is ideal, but we're going to pretend for class that the B field inside is totally straight and uniform and equal everywhere, and that there's no magnetic field outside. Well, how do we figure that out? Well, let's draw our little Amperian loop this way. So part of our Amperian loop you can kind of see is inside the box, and part of our Amperian loop is outside the box. Well, let's talk a little bit about our line integral side. We've got 4 sides to our box, which I'll number 1, 2, 3, and 4. If I look at my line integral along 1, I guess it's not closed if I'm just along that side. There's no magnetic field out there, so my line integral is nothing. For 2, I do have some magnetic field, but it is everywhere perpendicular to my curve, so my line integral is also nothing. Same for 4. So it's only 3 actually where I get my line integral equal to b times the length of my thing, which is L. All right, so my line integral is just b times L. Only one side of my box actually gave me anything. And that is, of course, equal to mu 0 times the charge, times the current enclosed, excuse me. Notice we've got a number of different turns inside. Our current actually passes through this box. Well, in this case, it passes through our box 1, 2, 3, 4, 5 times. We're just going to say that it goes through n times because they told us to. So we know that then we actually count it 5 times in this case. So mu 0 times I times n times that number of turns that we get to go through. So how many turns did we go through? We went through 5 in this case, but it could be more if we use smaller wire and wind it more tightly. And so what we find for a solenoid is that if we divide some stuff away, our magnetic field is equal to mu 0 times the number of turns times I, times the current, divided by the length of the solenoid. And sometimes instead we write n over L equals little n, where n is kind of, this is like, turns per meter. So it's like the turn density, I guess. But, basically if I make my, my solenoid with more and more and more wraps of wire, 10 times, 100 times, 1,000 times, I'm actually increasing my, the strength of my magnetic field. So if I double the number of turns, I double the strength of my magnetic field. So that's why solenoids can be very, very, very powerful. You find them in all kinds of things, from small electronic devices to MRIs and things like that. So this is also another one you're expected to be able to do with Ampere's law. All right, we're going to see more of this in class. But again, the magnetic field outside a solenoid looks like that of a bar magnet. Yeah. So again, let's talk a little bit just as a summary. We know that current gives rise to magnetic fields, and that we have 2 ways to find the direction of our magnetic field. If I have a straight wire, I point my thumb in the direction of the current. And the way that I like to think of this is the current is going in a straight line. So I put my thumb with whatever's going straight, and my fingers wrap to make the magnetic field. For a solenoid, though, it's the current that does the curling. So if I wrap my fingers with the current, my thumb tells me the direction of the magnetic field line. We can kind of practice that here. If I look carefully at my diagram, my current here is coming in the bottom. So it's going to come around the top, out of the page here, into the page here, out of the page here, into the page. So I'm kind of drawing my current here. So if I take my right hand and I curl my fingers so they come out towards my face on the top, in towards the page on the bottom, my thumb is going to be forced to this direction, which tells me which end the North Pole of my solenoid is. So we can use our right-hand rule, and we'll get a lot more practice on that in class. And we saw an example, 2 examples actually, of how to use Ampere's law. Similar to Gauss's law, and it tells us that that line integral, which again is either 0 or b times L, depending on the orientation of our field in our loop, equals mu 0 times the current enclosed. And we're going to pretend for our purposes here that solenoids always have a constant magnetic field inside and a 0 magnetic field outside.